Physical properties of metals. The physical properties of metals are hardness, luster, sonority, malleability, ductility, heat conductivity, and electricity. Hardness and luster. Metals are generally hard and rigid in nature because of closed packing of atoms in it. Let us understand it with the help of an activity. Take samples of iron, copper, aluminium and sodium. Note the appearance of each sample. You notice that all are silvery look and of shiny surface. Cut with knife of each of them one by one and notice. You will observe that only sodium can be cut by knife, but rest cannot be cut. From this activity we conclude that most of the metals are luster and hard except sodium and potassium. Both of these metals are known as soft metals. Sonority. Metals such as iron and copper produce a sound on being struck. Hence metals are said to be sonorous. Malleability. The property of metals by which they can be beaten into thin sheets is called malleability. Take some pieces of iron, zinc, lead and copper. Place any metal on a block of iron and strike it 4 or 5 times with the hammer. What do you observe? You find that some metals can be beaten into thin sheets. This property is called malleability. Ductility. The property of metal by which it can be drawn into wires is called ductility. Good conductors of heat. Take 4 iron nails. Fix each nail at some distance on an aluminium rod with the help of wax. Heat the rod with a burner near the place where it is clamped. What do you observe after some time? You will observe that the iron nail falls on heating. This activity shows that metals are good conductors of heat and have high melting points. Metals are good conductor of electricity. Set up an electric circuit as shown here. Collect the metals such as copper, silver and iron pieces. Place the metal to be tested in the circuit between the terminals A and B as shown. Does the bulb glow? Yes. In each case, the bulb glows. Thus we conclude that metals are good conductors of electricity. Physical properties of nonmetals. Nonmetals are solid, liquids and gases. The nonmetals are generally soft or brittle in nature. Take a piece of graphite and a crystal of sulfur. Beat them with a hammer. What do you observe? You will observe that graphite and sulfur break into pieces easily. From this activity we can say that nonmetals are brittle in nature. Nonmetals are not shiny and have a dull appearance. They are sonorous, malleable, ductile, poor conductors of heat and electricity. Reaction of metals with air. Let us explain this with the help of an activity. Take a magnesium ribbon and burn it. Collect the ashes formed and dissolve them in water. Test the resultant solution with both red and blue litmus paper. Is the product formed on burning magnesium acidic or basic? We observe that red litmus turns blue but no change in the blue litmus. Thus metals react with oxygen to give metal oxide. On dissolving it produces metal hydroxides. So it is basic in nature. Reaction of nonmetals with air. Nonmetals react with oxygen to produce their oxides which are acidic in nature. Let us explain it with the help of an activity. Take a small amount of powdered sulfur in a deflagrating spoon and heat it. As soon as the sulfur starts burning, introduce the spoon into a gas jar. Cover the tumbler with the lid to ensure that the gas produced does not escape. Remove the spoon after some time. Add a small quantity of water into the tumbler and quickly replace the lid. Shake the tumbler well. Check the solution with the red and blue litmus paper. You will observe that the red litmus paper remains unchanged, while the blue litmus paper turns red. Sulfur is a nonmetal and reacts with oxygen to produce sulfur dioxide or SO2, which is an acidic oxide. Reaction of metals with water. Let us explain with the help of an activity. Take a metal and put it in the test tube as shown here. Heat it and observe. You will observe that a gas is formed and gets collected by displacement of water in the gas jar. It shows that metals react with water and produce a metal oxide and hydrogen gas. Metal oxides that are soluble in water form metal hydroxide. Reaction of metals with water. Click on any button to know the reaction of water with different metals. Metals like sodium react violently with the cold water. The reaction is so violent and exothermic that the evolved hydrogen immediately catches fire. Magnesium does not react with cold water. It reacts with the hot water to form magnesium hydroxide and hydrogen. Potassium reacts violently with the cold water and the evolved hydrogen immediately catches fire. The reaction of calcium with water is less violent. The heat evolved is not sufficient for the hydrogen to catch fire. Reaction of metals with acids. Set up the apparatus as given here. Put granules of magnesium, aluminium, zinc and iron respectively in the Wolf bottle. Pour dilute hydrochloric acids with the help of thistle funnel and observe them. You will observe that the rate of formation of bubbles is fastest in magnesium and least in iron. The reactivity decreases in the order magnesium to aluminium to zinc to iron. This shows metals react with acids to produce hydrogen gas and corresponding salts with the different rates. Reaction of metals with solutions of other metal salts. Take a clean wire of copper and an iron nail. Put the copper wire in a solution of iron sulfate and the iron nail in a solution of copper sulfate taken in test tubes respectively. Wait for half an hour and then observe the color of the solution. A brown mass deposition on the iron and color of the solution changes from blue to green is due to the formation of iron sulfate. No reaction occurs between the copper and the iron sulfate solution. You notice that there is no change in the solution. Thus we conclude that reactive metals can displace less reactive metals from their compounds in solution or molten form. Ionic compounds. Let us explain. A sodium atom has one electron in its outermost shell. If it loses the electron from its M shell, then its L shell now becomes the outermost shell and that has a stable octet. The nucleus of this atom still has 11 protons, but the number of electrons has become 10. So there is a net positive charge giving us Na+. Chlorine has 7 electrons in its outermost shell and it requires one more electron to complete its octet. If sodium and chlorine were to react, the electron lost by sodium could be taken up by the chlorine. After gaining an electron, the chlorine atom gets a unit negative charge because its nucleus has 17 protons and there are 18 electrons in its K, L and M shells. This gives us a Cl-. The compounds formed in this manner by the transfer of electrons from a metal to a non-metal are known as ionic compounds or electrovalent compounds. Properties of ionic compounds. Impart color. Take the samples of sodium chloride, potassium iodide, barium chloride and strontium salts. Take a small amount of a sample on the metal spatula and heat directly on the flame. Observe the color. You will observe that the sodium chloride gives yellow flame test. Potassium chloride gives light yellow. Barium chloride gives crimson red, while strontium chloride gives an apple green color with the flame. From this activity we can say the different metals of ionic salts impart different colors with the flame. Physical nature. Ionic compounds are solids and are somewhat hard because of the strong force of attraction between the positive and negative ions. These compounds are generally brittle and break into pieces when pressure is applied. Electricity conduction in ionic compounds. Make a circuit as shown here and insert the electrodes and add sodium chloride. Switch on and observe. You will observe that the bulb glows. The NaCl solution dissociates into sodium ion and chloride ions. The conduction of electricity through a solution involves the movement of charged particles. A solution of an ionic compound in water contains ions which move to the opposite electrodes when electricity is passed through the solution. Ionic compounds in the solid state do not conduct electricity because the movement of ions in the solid is not possible due to their rigid structure. But ionic compounds conduct electricity in the molten state. This is possible in the molten state since the electrostatic force of attraction between the oppositely charged ions are overcome due to the heat. Thus the ions move freely and conduct electricity. Melting points and boiling points. Ionic compounds have high melting and boiling points due to the strong intermolecular force of attraction between the ions. Let us see. Click on one of the buttons. You will observe that the sodium chloride melts at 1074 Kelvin. Lithium chloride melts at 887 Kelvin, while magnesium chloride melts at 981 Kelvin. Calcium chloride melts at 1045 Kelvin. Solubility. Ionic compounds are soluble in polar solvents like water. Let us see. Dissolve the sodium chloride in water, kerosene and petroleum respectively. You will notice that the sodium chloride completely dissolves in water and is insoluble in kerosene and petrol. Thus we can say that ionic compounds are generally soluble in polar solvent and are insoluble in non-polar solvents such as kerosene and petrol. Occurrence of metals. Some metals like gold, silver and platinum are found in the free state in the Earth's crust because they are least reactive. Most metals are found as oxides, carbonates, sulfides and halides. Concentration of the ore is the removal of gangue or impurities from the ore by different methods. Following steps are involved in the extraction of metals from their ores. Extraction of metals low in the activity series. Metals which are low in the activity series can be reduced to metals by heating in the presence of oxygen. This process is called roasting. Mercury is obtained from its ore cinnabar, HGS, by heating in the presence of oxygen. When it is heated in the presence of oxygen, it is first converted into mercuric oxide, HgO, and on further heating, it is reduced to mercury. Copper is obtained from its sulfide ore, CuS, by heating in the presence of oxygen. Extraction of metals in the middle of the activity series. Metals in the middle of the activity series like zinc, iron, lead are found as oxide, sulfide and carbonate ores. It is easier to obtain metals from their oxides than from their sulfides or carbonates. Roasting is the heating of an ore in the presence of oxygen. It is used to convert sulfide ores into oxide form. Calcination is the heating of an ore in the absence of oxygen. It is used to convert sulfide ores into oxide form. The oxide ore is then reduced to the metal by heating with a reducing agent. The most common reducing agent is coke or carbon. Extraction of metals at the top of the activity series. Metals at the top of the activity series like potassium, sodium, calcium and aluminium cannot be obtained from their ores by simple heating or by heating with reducing agents. They are obtained by electrolytic reduction of their molten chlorides. When electric current is passed through the molten sodium chloride, sodium metal is deposited at the cathode and chlorine gas is deposited at the anode. Electrolytic refining of metals. Electrolytic method is the most common method for refining of metals. In this process, an anode is made of the large pieces of impure metal while a cathode is made of the thick sheet of pure metal. Put these electrodes into copper sulfate solution which acts as an electrolyte. Cathode connects with the negative terminal of the battery and anode connects with the positive terminal of battery. When current passes through electrolyte solution, the positive charge in the electrolyte gets attracted towards the cathode and converts into copper. As time increases, deposition of mass of copper increases on the cathode and electrode becomes thicker. As the metal ions move towards the cathode, the equal amount of ions are released by the anode in the solution. The soluble impurities goes into the solution, whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. Thus the copper is refined by this method. Thermit reactions. Sometimes reactive metals like sodium, calcium and aluminium are used as reducing agents to obtain metals from their oxides. The reaction between metal oxides and aluminium is highly exothermic and the metals are obtained in the molten state. Such reactions are called thermit reactions. The reaction between iron oxide and aluminium produces molten iron. This reaction is used to join rail tracks and broken machine parts. Corrosion. It may be defined as a process where materials, usually metals, are deteriorated because of a chemical reaction with air, moisture and chemicals. Let us explain with the help of an example. When the iron materials are kept in moisture for a long time, a brown mass is coated on the iron materials. This brown mass on the iron materials is called rust. Rust is explained with the electrochemical theory. When the iron materials are kept in moist condition, the cathodic and anodic regions are formed. The water vapors present on the surface of iron dissolve carbon dioxide and oxygen from air to form carbonic acid. So now the surface of iron is covered with carbonic acid. Carbonic acid dissociates to small extent to H+ ions. Iron in contact with carbon dioxide undergoes oxidation to ferrous iron with release of electrons. These electrons move through the iron metal and reach to the cathodic region. At cathodic region, H+ ions gain electrons to form hydrogen atom. These hydrogen atoms react with oxygen atoms to water. Thus in overall reaction, iron is reduced to ferrous ions. These ferrous ions react with oxygen to form ferrous oxide, which undergoes hydration to form hydrated ferric oxide. Hydrated ferric oxide is called rust. Corrosion of metals can be prevented by applying oil or grease, applying paint, by galvanization or coating with zinc, by tinning or coating with tin, by electroplating or coating a less reactive metal like chromium, and by alloying or making alloys. Let us explain some methods to prevent the corrosion. Plating. Let us see. Put some gold and iron in the gold solution. Connect the gold electrode with the positive terminal of a battery and iron electrode with the negative of the battery. When current is applied, the gold on the positive electrodes dissolves into the solution and gets attached to the surface of iron on the negative electrode. After some time we see that the iron is covered with gold. Galvanization. Galvanization is a method of protecting steel and iron from rusting by coating them with a thin layer of zinc. Put the iron and zinc in the solution. Connect the iron electrode with the positive terminal of a battery and the zinc electrode with the negative of the battery. When current is applied, iron gets covered with a thin film of zinc, which easily gets rust, but when it is exposed in air or water, it makes a layer of zinc oxide, which protects the rusting. To show that air and moisture are necessary for the rusting of iron, take 3 test tubes marked 1, 2 and 3 and put iron nails in each of them. Put some anhydrous calcium chloride in the test tube 1 to absorb moisture. Pour some boiled distilled water in the test tube 2 and pour some oil over it to prevent air into the test tube. Pour some water in the test tube 3. Cork the test tubes and leave them for a few days. You will observe that the nail in the test tube 1 does not get rusted because it had only air and no water. The nail in the test tube 2 does not rust because it had only water and no air. The nail in the test tube 3 gets rusted because it had air and water. This activity shows that air and moisture are necessary for the rusting of iron.